Hello and welcome back to lesson 6.9. We are working on part 2 now. This says the following is a list of conjectures made by students about right triangles and trigonometric relationships. For each, state whether you think the conjecture is true or false and justify your answer. So remember, the strategy here is always to try to disprove it. That's kind of our goal here. And then we will go from there. So go ahead and for the following 5, please try them out on your own and then tune back in when you're finished and we will have a look at them together. All right, number 5. So it says cosine A is equal to sine A. So think about this. It's the same reference angle, but it's cosine, which is adjacent over hypotenuse, and sine, which is opposite over hypotenuse. So you'd have to think about, okay, is there a right triangle in which this side and this side are both the same? That's the only way that this will work, right? So if there is, it would be an isosceles right triangle, and that should work, but all other right triangles will not. So it's false unless we have an isosceles right triangle. Now, number 6, tangent of A is equal to sine of A over cosine of A. So this one's a little tricky, but we need to think about, okay, what are all of these ratios? Well, I know tangent is opposite over adjacent, right? So I'm going to say opposite over adjacent, and I'm rewriting this here like this. And then I'm going to rewrite these as well by putting sine as opposite over hypotenuse and cosine as adjacent over hypotenuse. So I've got opposite over hypotenuse, bigger fraction bar here, and we've got adjacent over hypotenuse. All right, and then we have this fraction up on top being divided by another fraction, so we're going to do some math on it and flip and multiply. So we actually have hypotenuse over adjacent, and we're going to multiply these two together, and look at what cancels off. Hypotenuse and hypotenuse cancel off, and we're left with opposite over adjacent. So if we look back to what we're trying to equal it to, oh wow, look at that, it actually works. So that one is correct. All right, now sine A equal to cosine of 90 minus A. So let's think about what this thing right here means before we move on any further. If we're talking about a right triangle, we know that the right angle already is 90 degrees. And we also know that a triangle has 180 degrees within it when you add all of its angles up. So that means that when you're talking about these two reference angles that we have left, we only have A and B, and we know that they have to add up to 90 so that all the angles in the triangle can add up to 180 degrees. So if we think about this, this is saying A, and this is saying 90 minus A. But if we only have 90 degrees left to work with, then 90 minus A, won't that just be angle B? So really another way to say this is cosine of angle B, right? Because that's the only other place for those degrees to go is to be attributed to A, or excuse me, to be attributed to B. So if we look back up here, we know that if we have sine of A, that's actually going to be the same thing as cosine of B. So if we use that same thinking down here, we've got sine of A, and that's equal to cosine of B. So that one will actually work as well. So how about cosine of A equals sine of B? Well, actually, that's almost the exact same problem as the problem above. However, we're just using cosine. Ooh, I already forgot. Cosine of A and sine of B. So now we're looking at this one, comparing it to this one. Oh, check it out. They are the same. So that one works as well. And how about cosine of b equals sine of 90 minus a? Now, you might think, oh, we'll look right back up at number 7, and we already know that that's true. However, in number 7, we have a and 90 minus a, right? Making this one b. However, here we have b and 90 minus a, which really is referring again to b. And as we saw up in situation or case 5, right here, cosine A is only equal to sine A when we have isosceles, and that will actually hold true as well for B. So cosine B here will only be equal to sine B if we have an isosceles triangle. Right triangle, I should say. So only then. And then finally, tangent of A, is that equal to 1 over tangent of B? Well, let's have a look. So we've got opposite A over adjacent A. And here, I have to actually put my reference angle in so that I know what's going on, right? And is that equal to 1 over opposite B over adjacent B? So when I ever have a fraction in the denominator, I'm going to change that around to make it in the numerator. And so flip and multiply is what I'm doing. So I have adjacent of B, and I forgot my B right there, over opposite of B. So now I'm really comparing this one and this one. And if I think about adjacent B, that's really just the opposite of my angle A, right? And adjacent of A is just opposite, or is just the same thing as opposite B. Now let me go back up here and show you what I mean. If we have a reference angle here, our opposite side is going to be A. But if our reference angle is here, let me put this in a different color. If our reference angle is here, our adjacent side is going to be A, right? Whereas this reference angle, this is opposite. And here we have adjacent. So adjacent, opposite. Whereas here we have opposite and adjacent. So you can see when we change the reference angle, we're kind of changing our definitions a little bit. So when we're looking back down here, opposite of A is actually really just the same thing as adjacent of B. Adjacent of A is the same thing as opposite of B. So those are, in fact, equal to one another. All right, let's have a look here at number 11. That one's pretty tricky. Go ahead and try these on your own before we get started. All right, this one's a pretty big one. When we're talking about here and here, what they really are saying is that this thing, if we're looking at sine of A, which might be A over C, they're saying you could just square that whole thing, which would then make it A squared over C squared, right? And in the same idea, if we're looking at cosine of A, we would have B over C, square that, and that is equal to B squared over C squared. Okay, so let's use these, C squared. So let's use these two to substitute in for sine of A, sine squared of A, and cosine squared of A. And then we can reevaluate this. So when we're working with trig, this is one of our most handy tricks that we can use, is substituting in for the actual ratios that those trigonometric functions are representing. So we're going to try this. So all this to say, we're actually saying A squared over C squared plus B squared over C squared is equal to 1. We're trying to see if this is true or not. Now, I have common denominators in C squared, right? So I am going to write this in a single fraction. A squared plus B squared over C squared is equal to 1. Is that true? Well, here comes that theorem that we proved not too long ago. What is a squared plus b squared equal to? Well, thank you, Pythagoras. We know that a squared plus b squared is equal to c squared. So I'm going to substitute c squared there in the numerator. Guess what? C squared divided by c squared is in fact 1. There you have it. All right. I'll give you another second to look at that, have a gander, before we move on to the next one. All right, so now let's look at the second one. 1 minus sine a squared, or sine squared a, they're both the same, equals cosine squared a. So what we're going to do is actually we can create kind of a shortcut by eliminating all that stuff that we did up here, because we already proved that it is true, so we don't have to worry about that anymore. So I'm going to go ahead and erase all this. But I will say, because I know that this is true here, would it be okay to just do some algebra on that and say subtract sine squared a from both sides? Well, yes, whenever we have an equation, we can always do algebra with it. So another way to look at that would be cosine squared a equals 1 minus sine squared a, which is this thing right here. So we can say with some authority, yes, that is accurate because we already proved the previous equation, and since this is just a rearrangement of that previous equation, we can say that it is also true. All right, the last one is number 13. Go ahead and give that a try now that we've tried the others. All right, so we've got sine squared a equals sine a squared. Now notice where these squares are, right? This one is referring to the whole sine, whereas this one is referring to just the angle that we have in there. So now let's think about this for a minute. If we were to say that that angle is 30 and we're squaring it, do you think that that will be the same thing as sine squared of angle 30? Because this really will be saying sine of 900. Woo. Well, this one's just saying sine squared of 30, right? And so we're looking at the actual ratio here, the side lengths squared, not the angle squared. So this is not, in fact, a true statement, because this is squaring the side lengths, the ratios of the side lengths once we've found them, while this is squaring the angle itself before we've looked at any ratios. So there you have it.